Hello viewers, in today's class we are going to discuss yet another important application of Lagrange's mean value theorem, right? And here we'll make use of Lagrange's mean value theorem to prove an important inequality which is written over here, and here we have to prove this inequality using Lagrange's mean value theorem, right? So here what we have to prove, here we are given this inequality, that is ex divided by 1 plus ex, where e is the exponential number which is less than log of 1 plus ex, and that is less than ex, right, for all values of x greater than 0, right? So we'll prove this important inequality for all x greater than 0 using Lagrange's mean value theorem, right? So let us start. So viewers, before applying Lagrange's mean value theorem to this inequality, or to prove this inequality, what we will do, we'll first assume an appropriate function, right? So here let us first consider the function, say y is equal to f of x, which is equal to a log of 1 plus ex, right? And remember, when we are writing here a log, it means we are dealing with the natural log, right? So the same expression can also be written as ln, that is natural log of 1 plus ex, and here the base of the logarithm is the exponential number e, right? So here we'll prefer this notation, right? Okay, so here we have assumed this function, that is y is equal to log of 1 plus ex, right? So let us first see whether the conditions of Lagrange's mean value theorem are satisfied by this function or not. So let us see the first condition, right? So the first condition is that this function fx should be continuous for all x greater than 0, right? So here what we will do, let us take the interval that is 0 to x, right, where x is greater than 0, right? So in Lagrange's mean value theorem, what we usually do, we have a function y is equal to f of x defined in its domain D, and we take an interval a comma b, right? And we see whether this function is continuous or differentiable, right? So here we see that log of 1 plus ex is continuous for all x greater than 0, right? Because we know that the logarithm function is continuous in its domain, right? So here this function f of x, which is the log of 1 plus ex, is continuous in the interval 0 to x, right? And let us find out the derivative of f of x. So the derivative of f of x is f prime of x, which is d by dx of log of 1 plus ex, right? So here we are not writing the base, because it is understood that the base of the logarithm is e, right? So the derivative of log of 1 plus ex is 1 over 1 plus ex, because the derivative of log function is 1 over x, right? And by chain rule, the derivative of 1 plus ex is simply e, right? So we have e over 1 plus ex as the derivative of f of x, and we can see that the function f of x is derivable for all x greater than 0, right? So the function f of x is differentiable, right? So the two conditions of Lagrange's mean value theorem are satisfied by this function. So there must exist some point, say x is equal to c, where c lies between 0 and x, right? So there must exist a point x is equal to c where c lies between 0 and x, such that f prime of c is equal to f of b minus f of a divided by b minus a, right? So this is the result of Lagrange's mean value theorem, right, for some interval a comma b, right? So here our a is 0 and b is x, so this expression now reduces to f prime of c, and we have f of x minus f of 0 because a is 0 and b is x, and we have here x minus 0, so this is f of x minus f of 0 divided by x, right? Okay, now f of x can be obtained from the function itself, so we have log of 1 plus ex and minus f of 0. So f of 0 can be obtained from this expression by taking x equal to 0. So we have a log of 1 plus e times x, and x is 0, so we have e times 0, and we have here x, right? So now we can simplify this expression. So we have f prime of c is equal to a log of 1 plus ex divided by x, right? Because log of 1 plus e times 0 is simply log of 1, that is log of 1 is equal to 0, right? So now we have this expression, right? So now f prime of c can be obtained from this expression, because f prime of x is equal to e over 1 plus ex. So for x we can now write c, right? So now f prime of c can be written as e over 1 plus ec, and this is the log of 1 plus ex divided by x, right? So now finally we have this expression, right? So now to move further, what we will do, will use this inequality, right? See here, this point c, or this number c, lies between 0 and x, right? So let us multiply this inequality throughout by e, right? So if we multiply this inequality throughout by e, where e is the positive number, so we have 0, here we have ec, and here we have ex, right? Okay, so now see, here we have 1 plus ec, so what we will do, we'll add 1 throughout this inequality. So what we will have, here we'll have 0 plus 1, here we have 1 plus ec, here we have 1 plus ex, right? So this is 0 plus 1 is 1, here we have 1 plus ec, and here we have 1 plus ex, right? Okay, so now what we will do, we'll divide this inequality throughout by e, and again e is the positive number, so there will be no effect on the direction of the inequalities. So we have 1 over e, then here we have 1 plus ec over e, here we have 1 plus ex over e, right? And see, here we have e over 1 plus ec, so what we will do, we'll take the reciprocal of all these numbers, right? So the moment we will take the reciprocal of all these three numbers, so what we will get, see, we'll get e over 1, then the direction of the inequalities get reversed. So here we have e over 1 plus ec, and here we have e over 1 plus ex, right? So now we can rewrite this inequality as e over 1 plus ex, and we have e over 1 plus ec, and here we have e over 1, so that is simply e, right? And now for e over 1 plus ec, we can write log of 1 plus ex over x over here. So now we have e over 1 plus ex, and here we have log of 1 plus ex over x, and here we have e, right? Okay, so now we have this inequality, and see here x is a positive number, right? See here we have x greater than 0, so what we can do, we can safely multiply throughout by x, right? So when we throughout multiply by x, what we will get, we have ex over 1 plus ex, and here we have a log of 1 plus ex, because here x get cancelled, and here we'll get ex, right? So this is our desired inequality for all x greater than 0, right? So viewers, this is how by the application of Lagrange's mean value theorem we can prove this important inequality, right?